Module or Chapter 8, Electrical Power Generation and Distribution. Let's start with DC and AC electrical systems. Aircraft electrical systems provide power for avionics, which are different instruments, lighting, flight instruments. Avionics are, the controls, engine systems and engine detection systems, environmental controls such as the air conditioning, etc. Okay? So, depending on aircraft size and complexity, electrical systems may be direct current DC, which is a continuous current that does not change in amplitude in respect of time. So, its derivative is zero in respect of time. It doesn't change. There's no shift. And alternating currents, AC, where you have an alternating current going from positive to negative values, like a sine wave, okay, having a specific frequency, which is the inverse of the period. The period is the distance between two peaks or two troughs. Let me draw it. So that would be the alternating current, okay? The distance between two peaks or two troughs, that would be the period, of course, distance in respect of time. How many seconds? Okay, so the frequency is the inverse of that period, okay, and it's measured in hertz. So this is one of the characteristics of the alternating current, the frequency and the amplitude. The amplitude is the distance from the reference axis, horizontal axis, and the peak of the sine wave of the power signal, okay, or I'm sorry, the current signal. So DC systems are commonly used in light aircraft. Let me put back the laser pointer. So they are commonly used in lighter aircraft based on voltage of 14 or 28 volt architectures. Why? Because most of the controls are mechanical. They are directly correlated with the movement of the pilot controls, okay? So the pilot with his own strengths would move the ailerons, the elevators, the rudders, and smaller airplanes. So you don't need a higher amount of power, and DC is sufficient. However, in AC, in like larger airplanes, such as the heavy types, such as Boeing and other larger aircraft, AC systems are more prevalent in transport category aircraft, okay? Due to their efficiency in transmitting higher power levels and their compatibility with large motors or large engines and avionics. The fundamental relationship governing electrical power is P equal VI. V is the voltage and I is the current. Okay, that would be the power being generated by the engine or being fed to the engine. Okay, it goes both ways. Now, as a side note, when we spoke about the avionics, these are the systems in the aircraft that are used to control, navigate, communicate, monitor, and manage flight. Okay, think of avionics as the brain and nervous system of the aircraft. Now, within the formula that we've mentioned before, again, P is the electrical power in watts, V is the voltage, and I is the current. In AC systems, apparent power is defined as S equal VI. Okay? But real power, since you have a since you have a frequency, a changing frequency, real power would be given by P equal VI times cosine phi, where phi is the phase angle between voltage and current. Okay, so phi is not the frequency. Yeah, notice that and pay attention to the fact that phi is actually the phase angle between voltage and current. And here is what I mean by that. So let's say this is the current, and let's say this is the voltage, okay? So the voltage is in blue. Now, mind you that you have from here to here, from peak to peak, you have a full cycle, which is how much? It is 360 degrees. Okay? because this is the sine, correct? Or cosine, whatever you want to, you know, um, to cite it as. So you have, because they are no different, okay? The sine starts from 0, cosine from 1. Now, so let's say this current here, this is the current, okay? And one full cycle, which is from this point to this point, okay, or from peak to peak, or from trough to trough, that would be 360 degrees as an angle. Now the voltage in red, that's the V, okay, and also that's 360 degrees from peak to peak or trough to trough. Now the phase angle between voltage and current would be that distance here in terms of degrees, okay? So if you notice here, let's say this entire cycle, actually from peak to peak, yeah, this entire cycle is 360 degrees, right? Okay, from here to here. So here is almost at the middle. That would be around, if it's at the middle, it would be 180 degrees. So pi would be 180 degrees, and cosine pi would be equal to -1. I hope it's clear by now. 8.2 Generators and alternators. Generators and alternators convert mechanical energy from the engine into electrical energy. Okay? Early aircraft used DC generators, which are like the dynamo within your own car, while modern systems predominantly employ AC alternators due to improved efficiency and reliability. An alternator produces alternative current or AC voltage, which is often rectified to DC for distribution. The frequency of AC output is related to the rotational speed of the alternator, which is given by F equal, that's the frequency, P, or the number of magnetic poles, multiplied by N, which is the RPM or the rotational speed of the alternator, divided by 120. Okay, now voltage regulators control output, okay, the output voltage, by adjusting field current, ensuring stable power delivery, because we cannot have a fluctuation of the current that's being delivered to different instruments in avionics, okay? So it ensures a stable power delivery across varying engine speeds and electrical loads. 8.2 Generators and alternators. Generators and alternators are somewhat similar. They convert mechanical energy from the engine into electrical energy. However, early aircraft used DC generators, like this one to the right, while modern systems predominantly employ AC alternators due to improved efficiency, meaning that the rate of conversion from mechanical energy to electrical energy or power is more efficient, okay, so lower waste of mechanical power, and they are more reliable, which means that they can be sustainable, reproducing the same power results throughout their lifetimes. Okay, now an alternator produces AC voltage, which is often rectified to DC for distribution. The frequency of AC output is related to rotational speed, given by the following formula: F equal Pn divided by 120, with P being the number of magnetic poles and N is the number of rotations per minute, or RPM. Voltage regulators control output voltage by adjusting the field current, which is necessary to ensure stable power delivery across varying engine speeds and electrical loads, so that we wouldn't have a fluctuation of the current being delivered and the power, electrical power, being delivered to different components, instruments, and avionics. Otherwise, you might burn up or fry an electronic board. You might be risking doing that. This is why the regulators are necessary. if I may add another thing concerning the alternators, so unlike the generator which uses a commutator, these use slip rings, okay, in order to generate power. 8.3 Batteries and charging systems. Aircraft batteries provide electrical power during engine start and act as emergency power backup sources in the event of generator or alternator failure. By the way, the generator, DC generators, were used more commonly in smaller aircrafts. Meanwhile, the alternators are used in larger, heavy type aircraft such as Boeing airplanes. Common battery types include lead acid and nickel cadmium batteries. Battery capacity is expressed in ampere hours, Ah, which is given by Q equal I T. Y, actually, yeah, while T is the time. So let's say you have 200 ampere hours, meaning that if you supposedly you're consuming 2 amperes, okay, how many hours does this battery last? Okay, if we won't account for the losses, for how much the battery can be discharged, which is called DOD, or depth of discharge. Okay, so if it can be discharged to 90%, okay, and how much it can be filled up. So let's say it's 200 ampere hours. However, it can be filled to 95%, not more. So you multiply it by 0.95, okay, and it can be discharged 90% also to the lower, so you multiply again by 0.9. This is all that you can use, and you divide it by 2 amperes. It gives you how many hours it would last before it disconnects. Battery charging systems maintain power battery state of charge while preventing overcharging, which is important. Charging current depends on the difference between the generator voltage and battery voltage. This is the charging current. I equal the voltage of the generator minus voltage of the battery divided by R, which is the resistance. Proper battery temperature management is essential in order to avoid having an incendiary phenomena or event, as battery performance and lifespan are temperature dependent. Very important, okay? Because when you have an overheat, it would kill and depreciate the batteries rapidly. Bus bar and circuit protection. Okay, so what is a bus bar? Bus bars distribute electrical power to various aircraft systems, okay? So you have different electrical loads are grouped into main buses, okay, essential buses and emergency buses. These are the electrical connections among different, in order to distribute power for different systems. And these systems are grouped based on their own category and preference, of course. So this is like a distribution of buses, again, is based on the operational importance of different groups, with each group having systems that are like interconnected together. They have a dependent functionality among themselves. Circuit protection, when we talk about circuit protection, we're talking about circuit breakers and fuses. Now, the fuse snaps and becomes an open circuit when a specific current value is exceeded. So when you have a fuse of 2 amperes, for example, it would snap above when the current goes above that threshold, which is 2 or 2.2 amperes, depending on the tolerance. Meanwhile, the circuit breaker is like an automatic switch, okay, or like a thermosensitive switch that once the current exceeds a specific value, it would pop here, okay? It would pop to the outside, just like the circuit breaker you have in your house, except your own circuit breaker pops up and down. Here it pops outwardly when, uh, you know, the maximum current value that it can handle is exceeded. In fact, to be more accurate, when we talk about the circuit breaker that is used in residential application, it flicks rather than pops. This one pops to the outside when the circuit breaker is activated, and it opens up the circuit to prevent like an overheating of the cable or a potential fire. Okay, meanwhile the one at your house doesn't pop, instead it flicks upward. Okay, I'm sorry, it flicks downward when the current, the acceptable current is reached. Okay, so these devices operate based on the principle P heat, the power of heat, is equal to I square R. When the current exceeds safe limits, heat generated within the conductor that is on the circuit breaker causes the protective device to open, to pop the circuit, okay, to cut the current and prevent like a fire, a potential fire, or an overheating of the cables or the wires, rather. Bus architecture ensures that critical systems remain powered even in the event of partial electrical failure. Load management and redundancy. Load management involves controlling electrical loads to ensure power availability does not exceed generation capacity. Meaning, if the alternator is generating, let's say, 10 amperes, okay, this is like an example which is fictitious because much more power and current is required to run an aircraft, okay? But let's say, as an example, the alternator has the ability at some point, due to whatever circumstances, operational circumstances, to generate 10 amperes, okay? But the instruments that are running at that moment require 15 amperes. Okay, so automatically, in order to avoid having like a problem with the alternator, like burning or frying the alternator or breaking it, automatically non-essential loads would be shed, okay, would have their own circuit breakers pop up in order to throw them, okay, drop them from the load array, okay, or they can be manually shut down during abnormal conditions. Redundancy is achieved through multiple generators, independent power sources, and cross-tie buses. The total electrical load must satisfy the sum of all the load, the power of the load should be less than or equal to the power available. Otherwise, non-essential systems would be taken down from the power consumption, from the power array immediately and automatically via the intelligent mechanism of their circuit breakers. Okay? And even the electronic system would trigger that in order to ensure that there's no overconsumption of the power that's not available, okay? That would starve the different instruments and they would start working abnormally. And it even can risk, if there's no protection, surge protection, it can risk frying one instrument or two. Advanced aircraft employ electrical load management systems that monitor power generation, consumption, and system health in real time. Operational awareness and system limitations. Understanding electrical system architecture allows pilots and maintenance personnel to recognize abnormal indications, manage failures, and ensure continued safe operation. Electrical systems are designed to prioritize safety critical loads, the instruments that are the most essential for navigation and situational awareness, okay? And maintain essential functions under adverse conditions. What would be such adverse conditions? If the engine is no longer running properly, okay, the main engine, or if it flames out, then you would need, like if both engines flame out, you would need the deployment of the RAT or ram air turbine, which goes below the aircraft, and it would generate less power than the main engine, okay, which would require many of the non-essential instruments to be shut down in such case.